Hello, I am Burak Topçu. Today I will present a research paper that we named Predicting the Software Vulnerability of General Purpose GPU Applications. You can reach our GitHub repository from either this link or the QR code. Let me share the outline before going into details. I will start with a general overview by mentioning problem definition, motivation, contributions, and evaluations. Then I will explain our research framework, which consists of 4 parts. These are fault injection framework, performance metric collection, feature selection, and prediction model evaluation. Then I will share the experimental setup and experimental results. Lastly, I complete my presentation by sharing the conclusions, including our key contributions. We can state that general-purpose GPUs are prone to soft errors due to their complex structures. This figure represents a soft error. Soft errors result in transient errors because of a fault in a single bit. This fault is caused by particle strikes, cosmic rays, and electrical noise. To prevent these errors, vendors implement some techniques from both software and hardware levels, such as redundant multi-threading. Also, recognizing software vulnerability of a GPU application requires lots of fault injection experiments, meaning that developer needs to spend too much time. Our motivation is to find a way to determine software vulnerabilities of general-purpose GPU applications easily instead. So our contributions consist of experimenting a fault injection tool, obtaining the profiling results of general-purpose GPU applications via both simulator and profiler, associating relations between metrics and fault rates, selecting the most relevant metrics for prediction experiments, predicting the fault rates with classification and regression approaches. Eventually, we observe 96.5% prediction accuracy from regression experiments and 80% prediction accuracy results from 2-class and 3-class classification experiments. At the first stage, this is our study framework, which includes 4 main subparts. At the first stage, we inject faults to the GPU programs. Then we obtain resultant errors if they exist as SDC, silent data corruption, and crashes. Faults can also be masked. At the second stage, we collect 2 sets of performance metrics from simulator and profiler. The reason why we use 2 different profiling platforms is that we want to decide which type of metrics are more useful for predictions, such as hardware usage metrics or performance and instruction metrics. At the third stage, we select some of those metrics as features according to the correlation results. With this stage, we enhance our prediction accuracy rate. The correlation methods that we use, Spearman and Pearson correlation methods. At the last stage, we apply our regression and classification tests to these algorithms to predict the fault rates. Actually, this is a flow diagram of our regional fault injection tool. Fault injection starts with a configuration of fault injection. In the configuration stage, the user specifies the fault injection location in the code. Afterwards, the GPU algorithm is profiled with the CUDA debugger, which is CUDA GDB, to determine the PDX code, number of active thread blocks, and threads. Then the fault map is created. At this stage, the algorithm is ready to inject the fault, and the following step injects faults by flipping a bit of a register. At the last stage, the results are obtained and fault type is determined by comparing the fault injected output and golden output. The fault types are silent data corruptions, crashes, and masked faults. In this slide, the pre-selected metrics are shared. The left table shows the metrics obtained from the simulator. Simulator mostly provides performance and instruction metrics such as IPC rate, instruction amount, and intensities. The right table shows the metrics obtained from the profiler. Profiler mostly provides hardware usage metrics such as SM throughput, compute memory pipeline throughput, L1 and L2 cache throughputs, DRAM throughputs, etc. After collecting the metrics, we need to eliminate the irrelevant ones. To do so, we benefit from Spearman and Pearson correlation methods. While Spearman correlation shows a monotonic relationship, Pearson correlation describes a linear relationship between fault rates and our metrics. We select our metrics whose either Spearman or Pearson correlation result is greater than 0.2. For example, Sol SM metric for the crash faults have a correlation result which is greater than 0.2. Hence, we select this Sol SM metric as our feature. The other metrics, the other selected metrics are listed in this table for each fault type. Similar situation is valid for the simulator metrics. This figure represents the correlation results obtained with the simulator metrics and fault type. And this table lists our selected metrics. For example, load instruction for the crash faults. Load instruction for the crash faults with Pearson correlation results has a correlation value which is above 0.2, and the other metrics are selected in this manner. You can reach the selected metrics from our GitHub repository. And lastly, we built 3 regression and 3 classification algorithms to predict masked faults, SDC, and crashes respectively. Our first model is the random forest model. This algorithm builds multiple trees where classification from different trees. At the end, there will be multiple prediction results, and average of these prediction results is our fault prediction. These are the main hyperparameters for the random forest algorithm. The second algorithm is the support vector machine algorithm. This algorithm tries to build a kernel function to capture all of the samples with a margin. This margin is specified with this epsilon value. Margin, our kernel function can be linear, sigmoid, or polynomial. We specify this kernel function type at the beginning. We can also specify the degree of our function type, for example, polynomial function. Also, we have gradient boosting algorithm for the regression experiments, also the classification experiments. This algorithm builds an initial model, as you can see, a decision tree. We set a number of repetitive stages, and each of those stages are multiplied with a learning rate. This learning rate is specified at the beginning of the skeleton of the function. By correcting the repetitive stage with losses, we try to achieve the most accurate prediction rates. Each boosting stage enhances the gradient boosting algorithm more. Lastly, the last algorithm is obtained by cascading standard scalar and stochastic gradient descent algorithm. SGD algorithm tries to classify data samples with a function similar to the SVM. This function is guided with the loss, different loss actually, from the SVM function. Also, we have L1 and L2 regularization penalties for SGD algorithms implemented in Python scikit library. Since these regularization methods is used commonly in neural networks, we think that these regularization will be useful for our predictions also. In our experiments, we experiment with the algorithms selected from the Polybench benchmark suite. The algorithms includes common mathematical operations such as matrix multiplication, convolution, correlation, and covariance operators. The graph shows the rates of faults with respect to the others. As you can confirm, masked faults are most common fault type compared to the other faults. Also, instead of predicting the fault types in an CUDA application level, we carry out our tests based on a kernel level. For example, correlation CUDA correlation GPU application has a has 4 different kernels, etc. In our experiments, we use GPGPU simulator to collect performance metrics. In the simulator, we try to set hardware parameters as in Quadro P4000. Also, fault injection experiments and profiling experiments for the other metric collection are done on NVIDIA's Quadro P4000 GPU. For the profiling stage, we have used NVIDIA's Insight Compute tool. This list shows the specs of our GPU. This formula shows our accuracy calculation formula. We are calculating accuracy as percentage. We experiment prediction of masked fault rates with 12 different configurations, including 3 different regression algorithms and 4 different feature sets. Resultant from these experiments, the highest accuracy result, which is 96.5%, is obtained with the simulator metrics, as you can see. For the classification experiments, we divide SDC and crash faults rates by 2 and 3. For 2 classification experiments, the highest prediction accuracy results are 87% and 82.6% for crash and SDCs respectively, as you can confirm. These results are obtained with the simulator metrics. For 3 classification experiments, the highest prediction accuracy results for SDC faults, 80%, obtained with the profiler metrics, as you can confirm. We could not observe meaningful prediction rates for crashes with 3 classification experiments, as you can see. Also, as you can confirm, simulator metrics are more useful for the prediction experiments because of its deterministic structure. I mean, profiler metrics is not as successful as the simulator metrics to predict the fault rates for our GPU, general purpose GPU applications. To conclude, our goal is to predict the fault tolerance of general purpose GPU applications, providing reliability for these applications and decreasing the effort and cost of the precautions that I mentioned previously. Most of the faults are the masked faults, as I shared a previous slide, and most of these faults are predictable with our regression methods. Masked faults are predicted at 96.5%, SDCs are predicted at 82.6%, and crashes are predicted at 87% at these accuracy levels. To conclude, masked faults can be predicted with the regression models. Furthermore, developers can eliminate most of the SDCs and crashes by noticing the vulnerabilities to these errors via 2-class and 3-class classification experiments by benefiting from the metrics from both simulator and profiler.